Okay, so welcome back to another week, our last week before spring break, so that's exciting. Something I don't want to forget to say is remember that we have the midterm exam this week. So, as I mentioned in previous announcements and so on, and previously in the course, the midterm exam is open this whole week. It's open from this morning through this coming Sunday at 11:59. Do not wait until the last minute to take the exam. Had a couple of other sections where other courses where the exams were the last couple weeks, and unfortunately, somebody waited until the last minute to take the exam, had some tech problems, and ended up not being able to take it. And given that missing a whole exam is going to drop you down to a best case scenario 70%. That's really not a position you want to be in. So schedule a time for the midterm exam. Make sure that you've gone in and taken the Examity practice exam so you understand the Examity process. Get the account set up, get all the tech working, just make sure everything is working right. And then take the midterm exam at least a day or two before the due date. So that way, if anything pops up, if there's any tech problems, there's time to get things sorted out before the due date and time. There are no extensions on the due dates for the exams. I know one of the questions that was asked in chat was kind of how close the sample midterm exam is to the actual midterm exam. And I would say it's quite close. So if you take the sample midterm exam, if you take it in kind of roughly a similar fashion to how you'll take the midterm exam, so with the same resources, calculator, Excel, those kind of things, but not with another person next to you or looking things up on the internet. If you time yourself, you give yourself the amount of time, the 100 minutes that you'll have on the exam. If you kind of set yourself up in that environment and did well on the sample midterm exam, then you should be pretty well prepared for the actual midterm exam. If you went through the sample midterm exam and there were a couple problems or a couple of topics that you really struggled with, or that you felt took you too much time, or that you didn't get correct, that might direct your studying. It might show you what topics might be higher yield for you, what you might want to hit a little harder on your studying, and the parts that you felt really comfortable with, maybe you can focus a little less on those. So that's how I would recommend using the sample midterm exam. Just a reminder, there's the Examity practice exam that is password protected. It is to be taken through Examity and all of that, just like the regular exam. That's just to get you set up on Examity. It's got a couple of like dummy questions in there just so that there's something in the exam. But the sample midterm exam, you don't have to take it through Examity. You can take it as many times as you want, but that's really to practice the stat side of things. So that sample midterm exam, that exam will be very similar to the actual midterm exam. Obviously, the Examity practice exam that just has a few random questions that I threw in there just so that there's something in the exam for you to navigate around and do. That is obviously not going to be similar to the content of the midterm exam. That's just to practice the Examity process.
So the midterm exam is gonna be in Examity or in my stat lab? Because the sample of midterm exam it's in my stat lab. So
Yeah, so again, if you haven't gone through the Examity practice exam, I would recommend watching the videos that I posted and going to the links that I posted and going through the Examity practice exam. The Examity practice exam has been up for a few weeks already, and that will make the process much more clear. But kind of the short version is that Examity is the proctoring system, and my stat lab is the system where the exam is taken and hosted. So you'll basically log into Examity, get the session started up, get like the webcam recording and screen sharing and all that started up. You'll go and then you'll log into my stat lab, and then you'll open the exam in my stat lab, and then Examity will enter the password into the my stat lab exam, and that'll unlock the exam for you. So you'll take the exam in my stat lab, but it will be proctored by Examity. So it's a little bit kind of confusing getting these two sides to work together. And that's really the purpose for the Examity practice exam, is to go through that process once. And kind of once you go through it once, you kind of see how everything fits together. but it's really hard to kind of explain in words. But again, if you go through it once, you kind of go into Examity, get the proctoring session started, go into My Stat Lab, log into your account, get the exam opened up. Examity will enter the password into My Stat Lab, and then you can take the exam on My Stat Lab just like you would, be taking the sample midterm exam or completing a homework or something like that. Very similar feel. So the My Stat Lab stuff will be all the same. You'll just have Examity running in the background as the proctoring system. And then of course, when you're done, you just close out of everything
Okay, that's what I wanted to make sure, because I did work on the sample of midterm exams, so that's how it was, that you have to go through Examity to My Stat Lab. I just wanted to make sure because the exam started on them My Stat Lab, so I was kind of I wanted to make sure that I'm doing it right.
Yeah, definitely. So the sample midterm exam with like a whole bunch of questions in it, that you don't have to go through Examity for, because number one, we have to pay for each Examity session. So I don't want, and number two, that's just kind of annoying for you to have to go through all of that to open up the sample midterm exam. So you can just do the sample midterm exam on My Stat Lab and take it as many times as you want. But for the Examity practice exam and for the actual midterm exam, you will have to do the like Examity and then over to My Stat Lab kind of thing. So yeah.
Okay. And one more question. How is
Sure.
this proctoring mean? Because it's my first time on this kind of an exam. So I want to have like some more information. Is it like, what does proctoring mean? Or like, do we have someone watching us, or it's
Yeah. So good question. So with Examity, there are a couple of different options, and depending on the instructor, they can pick different options. So there is a live proctoring option where there will be a person that you interact with, but we're not using that. Some instructors choose to use that. So in other courses, your experience might be a little different. I found that there tends to be a lot of technical problems and other kind of problems with that system. So we're just doing an automated proctoring system. And all that means is that when you log on to Examity and start the session, it will ask you to share your webcam. So your webcam that'll, point at you, and it'll ask you to share your screen so that like what you're looking at on your computer screen will be recorded as well. So the webcam will record, the screen will record. And then after you get that kind of going and set up, you can just forget about that. You can just, once that's going, there's nothing else you need to do to keep it going or anything. You just log into My Stat Lab, you just take the exam, and then that recording will be saved on Examity's servers. And then I'll go in later on and I'll just kind of take a glance through. Just as a side note, Examity flags all kinds of random stuff. It'll say like, oh, suspicious eye movement is one you get all the time. Like if somebody looks away from the screen or something, if you get a flag or something, that doesn't mean anything. I'll go through and look through it, and almost all the time those flags just are meaningless, and it's just like, oh, okay, Examity's auto detect system is just, well, now that we have the vocabulary, it's very sensitive but not very specific. So it's more likely to call something as suspicious, even if it's a false positive, than it is to let something suspicious go by and risk a false negative. So if you get a flag or something, that's not a big deal. That's just their automated system. But again, I'll just go through and kind of look through the recordings afterwards. And, very rarely is there any kind of a problem. I won't say never, but it's quite rare. So that's how the proctoring works. It's just an automated system.
Okay, got it. Thank you so much.
Yep. Yeah, sure. Any other questions about the midterm? The material is from the beginning of the semester up through and including Bayes' theorem. So that's the material for the midterm. And then chapter 6 and later will be that'll start the material that'll be on the final.
How many questions there would be?
Off the top of my head, I don't remember because I have so many courses, but it is in the announcement. So if you peek back at the announcement, or if you look in the sample midterm exam, the number of questions is about the same.
Oh, okay.
Yeah, I have too many too many courses. All the exams are different weeks and different dates, and and different lengths too. So off the top of my head, I don't quite remember, but yeah, it'll be very similar, you know, essentially the same number of questions, possibly plus or minus one for the sample midterm exam. All right, let's do our quote of the day and then on to the next topic, continuous probability distributions. So the quote of the day, attributed to Albert Einstein. I'm always hesitant to say that Einstein said certain things because often these things get attributed to him, and it's spurious at best because people think that the quote carries more value if it's attributed to somebody, you know, that everybody knows. But there's this statement: everything should be made as simple as possible, but no simpler. So where does this apply to something like stats? Maybe that we want simple models, but if we pick models that are too simple or overly simplistic, they don't do a really good job of modeling what we're trying to model. On the other hand, if we pick models that are too complicated, they still might not do a good job modeling what we're trying to model, or even if they do a better job, we might not be able to understand them very well and build off of them. So this kind of these degrees of complexity we can see in things like, you know, F equals ma from physics. It's super nice, super easy to understand. We can build a ton of physics off of just these couple of ideas from Newton. But maybe it doesn't reach into the quantum world or the kind of galactic world, the relativistic world so well. So maybe it has some shortcomings. We could have more complicated models, like say quantum mechanics, that's super complicated, but is like super hard to understand or to get an intuitive feel of. I think it was maybe Feynman or one of these famous like guys who was really good at quantum mechanics. He said something like, you know, you never understand quantum mechanics, you just get used to it. So there are these two extremes. And I think in artificial intelligence today, we have models that, at least in some sense, are extremely complex, that do a very good job of answering questions, but they can be very hard to build off of because we don't understand how they're actually answering those questions. I mean, we understand the theory behind it, but not, you know, not what all the little pieces of the computer program, in a sense, are doing. And in a practical sense, if you're thinking, say, like solving an algebra problem, it's always a good idea to reduce complexity before increasing it. So I like to think of kind of if we have, you know, steps and complexity, I would much prefer to do something like this to get to my answer than to do something like this, right? I don't want to, say, try to expand all of my terms out and then work with this huge gigantic thing. I want to do things like expand a little bit, combine all my like terms, you know, expand a little bit, combine all my fractions together, get everything under a common denominator, things like that. Like I make it a little more complex and then I try to simplify, a little more complex and then I try to simplify. I don't want to, you know, go complex and get this hugely cumbersome thing to deal with and then try to simplify it all on the other side. I want to simplify kind of every chance I get. That's why, you know, since whatever 8th grade or something, your teachers have made such a big deal about simplifying everything, simplify the fractions and combine all the like terms and, you know, simplify the expressions and all this kind of stuff. We want to just get in the habit of doing that after each step. It makes the process much easier. And also, as a general notion, difficulty scales non-linearly with complexity. If I double the complexity, if I double the number of things that I have to keep in mind and handle in a given step, the difficulty doesn't double, it much more than doubles. So when I have a more complex system, it becomes much more difficult for me to deal with. And I think this applies to life as well. If you're going into a situation that's going to be a somewhat complex situation, like my sister and her family about a year ago moved back to the US from Northern Ireland, where they lived for 5 years or so. Like that's a very complex situation, right? You want to minimize all of the other complexity that surrounds that. You don't want to throw additional complexity on top of that already very complex move, because that's going to make the difficulty intractable. Okay, so let's move on to continuous probability distributions. This quote particularly applies today because we'll see that relative to discrete probability distributions in chapter 5, continuous probability distributions are going to be more complex. They're going to be less simple. But I think they're going to be as simple as we can make them. So because of the additional complexity, we're also going to have to take some, I might call it something like a shortcut, some kind of ends around. We're going to have to use some additional help, and we'll see what form that will be in a little bit here when we talk about the normal distribution. But let's start the discussion of continuous probability distributions. And let's start from the perspective of a discrete probability distribution. So what did a discrete probability distribution look like? It looked like, and let's just consider that we have finite number of outcomes. It looked like a list of outcomes with their associated probabilities. And we had kind of mentioned that we can think of these outcomes as kind of locations on an axis in these probabilities, like masses at those locations. And we said, for instance, we could find the expected value, which we could think of as like the center of mass. Maybe here it would be something like here. The kind of balance point, if we imagine this horizontal line being a weightless rod with these masses, these locations, where would this balance? The expected value of x finds that balance point. It's the mean of the distribution. And again, we were thinking of these as being like masses. Mass as in like, weights. We also noted that mass as in weight, like physical weight, also kind of related to the expected value, right? I guess I just have 4 of them here. We just have our outcomes that are weighted together. This is a weighted mean. So these probabilities in the kind of physical sense act like actual weights on a bar, and in the algebraic sense, in the more abstract sense, they act like weights applied to the different components of a weighted mean. Okay, so let me think for a little bit about let's forget about this physical side of things for just a minute, and we'll think about, say, a histogram. And if I think about a histogram, I might have some bins, right? These bins could be like somewhat equivalent to these outcomes. I could be in bin 1 or bin 2 or bin 3 or bin 4. I could be in a certain bin if I have discrete quantitative data, right? I could also kind of be in a certain bin if I had continuous quantitative data. So what about continuous quantitative data? I could construct certain bins. So let's say, for instance, that I was thinking of a person's height. I could construct a histogram and I could say well, maybe from 5 foot, I don't know, 1 inch or something to 5 foot 2 inches, I can make a bin there. And I have this many people, this frequency in this bin. For the folks between 5'2" and 5'3", oh, sometimes OneNote tries to be too smart. For the folks between 5'2" and 5'3", they would fall into this bin. And I have this frequency allocated to this bin. So I'm choosing to set my bins up as 1 inch wide. And when I set up my bins, I can sort my continuous data into these bins. These bins should be set up so that each potential data point falls into exactly one bin. So no data point is going to fall into two bins at the same time, and no data point is going to not fall into any bins. But maybe I have, a histogram that looks like this. Maybe it's bimodal. I don't think it will be this strongly bimodal, but it makes an interesting picture anyway. And okay, so here are my bins and my histogram for, say, the heights of people. I could kind of think of this as a discrete probability distribution, right? I could think of this as kind of being discrete, just taking maybe the midpoint and just saying, pretend that all of the heights between 5'1" and 5'2" are 5 feet 1.5 inches. Just label all of those folks as 5 feet 1.5 inches tall. And that's my first outcome. It has a certain frequency or probability associated with it. And then the folks between 5'2" and 5'3", call them 5 feet 2.5 inches tall. That would be my next outcome. It has a certain frequency and so on, right? Certain relative frequency. But now I might say to myself, okay, well, I chose bin widths of 1 inch. I have to approximate. Maybe I want to get a little bit nicer of a histogram. Maybe I want to refine this a little bit. Maybe I can double the number of bins that I have so that each bin is 1/2 inch wide. I have twice as many bins. Each bin is half as wide. And then I can kind of reassort the people. So the folks in the 5'1" to 5'2" bin, some of them will end up in the 5'1" to 5'1.5" bin. And some of them will end up in the 5'1 1/2" to 5'2" bin. So I could split this bin in half. Some of those folks are going to go on the left side, some on the right side. Maybe it looks like this. I could do the same here. Maybe it happens to look like this. I could do the same and the next one, and so on. I'm not going to draw all of these. I'll just draw this many. And let's just forget about the right side for now. Let's also forget that we're dealing with heights here. We'll just abstract away from the specific case of heights. Let me see if I can zoom this in a little bit. There we go. Should play the lottery today. OneNote's zooming and copying and so on is working well. So now I have my green bins. There's twice as many green bins as there were black bins, but each one is half as wide. So each bin is a little less likely to be fallen into. So say on average about half as likely to be fallen into or to be occupied by somebody, but there's twice as many of them. I suppose I could do this again, right? I could divide each of these green bins that are already smaller. I could divide each of them in half. And I would get a more refined curve. Now it's starting to just look like a jumble of different lines. But we could kind of imagine that if I do this, 10 times or 20 times or something, keep dividing in half, I would get something that would look like very close to a nice continuous function. And as I let the number of bins go to infinity, still in this finite range, but if I just keep subdividing the bins over and over and over, so I work my way toward infinitely many bins, and I let my bin width go to 0, I move toward a continuous function. Instead of a piecewise constant or a step function, I move toward a nice continuous curve that in some senses, in some ways, related to those underlying discrete probability distributions, but is kind of fundamentally different. Once we start throwing around infinities, things get a little more complicated. Okay, need a little more room here. So now let's go back to the coarse black bins. Something like this. And here I can say that if my bin width is, say, maybe 1 unit wide, and it has a height, say probability of x1, then the area of the bin is actually probability of x1. If I were to cut the bin width in half, and it kind of maybe on average stays the same height, then the area of each of these smaller bins gets cut in half as well. But we would expect that, right? The probability of fitting into the smaller bin is going to be, say, something like on average half of the area of fitting into the larger bin. So this is the first key concept here. We're going through all of this background to realize a couple of important things. Number one is that probabilities are related to areas in continuous distributions. So when we have a two-dimensional graphical representation of a probability distribution, if we have a discrete probability distribution kind of in roughly this sense, where we're dealing with a histogram type of thing with grouped data, well, our probabilities correspond roughly to areas there, provided we set things up properly and so on. But if probabilities correspond to areas in this kind of a setup, if I subdivide my bins in half and do that again and again and again, probability should still correspond with areas. So even when our number of bins goes to infinity, our bin width goes to 0, and our function that defines this two-dimensional structure, instead of looking like a piecewise constant function, instead of looking like a step function, if it looks like a nice smooth curve, I still think of probabilities as being related to areas. So this is the first super important concept when we move from chapter 5 into chapter 6, is really rethinking about probabilities as areas. It's not that we couldn't have thought of them as areas in chapter 5. That was, that wouldn't have been a problem. It was just less helpful. It was more helpful to think of them as kind of masses and so on. But here it's more helpful in chapter 6. It's more helpful to think of probabilities as areas, as two-dimensional areas. What else might we want to say? So let me say that now x is a continuous random variable, something like the height of a person or the temperature of a room or something like that. Something where there's not a natural next option, right? If you talk about number of students in the classroom, you could have 0, or you could have 1, or you could have 2. There's a next possibility for each for each option. If there are 0 students in this classroom, what would be the next possible outcome? Would be 1. What's the next possible after that? There's 2. If I say this person is exactly 6 feet tall, what's the next possible height? There's not a next possible height. We might say 6'1", but somebody could be 6.5 feet tall. Or we might say 6 foot and 0.1 inches tall, but somebody could be 6 foot and 0.01 inches tall. They'd be in between those two. There's not a next concept. If we have a continuous random variable x, what's the probability that, for instance, x equals c, some number? The probability that a person's height is exactly 6 feet tall. Well, our bin widths are going to 0 when we move into the continuous case. This person might be close to 6 feet tall, but when I start subdividing the bins near 6 feet tall, when I start cutting them in half and in half and in half again, what's the chance that they stay in the bin that contains 6 feet tall? It gets smaller and smaller and smaller, right? Maybe when I had a bin that was like 6 feet 0 inches to 6 feet 1 inch, they were in that bin. Or let me make it a little easier. I guess we can just stay with this. And I'll just put the inch marker here. So what about 6.5 feet an inch? Do they stay on the left or do they end up on the right? What about when I divide that in half again to the 1/4 inch? Do they stay on the left or do they end up on the right? When I divide again, do they stay on the left or end up on the right? When I divide again, right, as I keep dividing, there's a chance that they end up on the right of one of these bins and not on the left. They would have to kind of end up on the left side infinitely many times through infinitely many divisions as the bin width goes to 0, as the number of bins goes to infinity. What's the chance that somebody, if you flip a coin and you say heads means they're on the left side and tails means they're on the right side, if you flip a coin infinitely many times, what's the chance that you get all heads? It's got to be 0. That's kind of the question we're asking here. This probability is 0. So let me erase some of this. And then let's redraw the distribution with just this continuous function. So this is the function that we get after the number of bins went to infinity, the bin width went to 0. We get maybe a bell curve that looks something like this for heights. And this actually kind of makes sense, right? If I say, what's the probability that a randomly chosen person is between 6 feet tall and 6'1" tall? Maybe this is where 6 feet tall is located on my axis, and maybe this is where 6'1" tall is located. I can say, okay, that probability is that area that I've just shaded in. Maybe it's 3% or something, whatever it is. This is certainly not to scale. I don't think there are that many people who are between 6 foot and 6'1", but just for illustration. But then if I ask a question like, what's the probability that somebody is exactly 6 feet tall? What am I asking? If 6 feet tall is this location on my horizontal axis, I'm asking what's the area of just the vertical line? That area, of course, is 0. It's a little bit like a rectangle with 0 width. So strangely, in a continuous distribution, the probability x equals any specific number is 0. Note that this is very different from a discrete distribution. If we roll a six-sided die, fair six-sided die, the probability that we get a 2 is like 17-ish%. It's not 0. But for continuous, because we let the number of bins go to infinity, the bin width went to 0, the probability that we get any specific number from a random variable is 0. So really, we're interested in questions about probabilities of ranges of numbers. We're interested in events like say probability that x is between a and b. That's kind of an interesting probability. It doesn't mean we can't ask what's the probability x equals c. It's just always 0. So that's just not super interesting. But if we ask what's the probability x is between a and b, between two numbers, that's going to give us, typically anyway, it's going to give us an area that's non-zero, and that's maybe an interesting thing to know. Or I could ask, what's the probability x is bigger than a, right? What's the probability somebody's taller than 6 feet 2 inches tall? That would also be a region, right? That's going to give me an area, at least most of the time. That's probably going to be an interesting question to ask on occasion. Or probability x less than b is also similarly going to be an interesting question to ask on occasion. So typically, we're not going to ask what's the probability that a continuous random variable is equal to some number. We'll ask one of these three questions. Again, it's not that it's nonsense to ask what's the probability that, somebody is exactly 5 feet 8 inches tall. It's just that the answer is always 0 in this context. So it's not interesting. And again, for we're taking the exam this week, so I don't want you to get the ideas jumble. In discrete probability distributions in chapter 5, probability x equals c is a very valid question to ask. It's a question that we quite often ask and are quite often interested in. So we're really shifting gears here. In a sense, we're very much shifting gears. It feels a lot different, but in a sense, the underlying structure is really just built from the same details. Okay, so one more thing that I want to mention, give myself a little more room down here. In our discrete probability distribution, we had something that looked like this: outcomes versus probabilities. And our continuous probability distributions, we have, and maybe I'll actually come over here just for consistency and draw these probabilities as red. Over here in continuous probability distributions, we have a smooth curve like this. It's not always going to be a bell-shaped curve. I just tend to draw bell-shaped curves because we'll see normal distribution, the bell-shaped curve comes up a lot. So we might note that this is actually kind of two ways to represent a function. I could enumerate the inputs into the probability function, so to speak, and enumerate the outputs. This is a tabular representation of a function. I have outcomes that go into the probability operator, and it pops out a number. Over here, I have a graphical representation of a function. I have a two-dimensional picture that has an input, my location horizontally, associated with an output, a certain vertical number that's associated with that horizontal input. So over here, we call this a probability mass function. We didn't call it this in chapter 5 because we didn't really have a reason to distinguish between these two ideas. But now that we're in chapter 6, this idea might come up, the idea of a probability mass function or a PMF. And again, this ties to me thinking about these probabilities as physical masses or physical weights, which also ties to the things like the expected value being a weighted average and so on. Now I have a little bit of a problem. If I wanted to call this curve here a probability mass function, but the probabilities that are related to this curve are actually areas under the curve. So it's not saying that for this input, I get this number as the output, this y value or this vertical value as the output, and that's my mass at this location. No, because mass corresponds to area. If I wanted to force an idea of mass, I would have to take some narrow kind of range around my horizontal point of interest, find the area under the curve above that horizontal range. And then I would have to take this as the mass. But how big should the range be? Should it be to the left or to the right? That's not really clear. But what I do see is that I need to accumulate points in order to get mass. I need to accumulate, in this case, horizontal distance in order to achieve mass. So what does this red curve represent? It represents something like mass in the sense over here, or probability per unit horizontal distance per unit distance. If I had mass per unit volume, say in a 3-dimensional structure, what's mass per unit volume? Well, mass per unit volume is a density, right? Like kilograms per cubic centimeter or something, or grams per cubic centimeter. That's a volume. That means I have to tell you how many cubic centimeters of the thing I have, and then I can tell you how many grams it is, what the mass is. Mass per unit distance is just a linear density. This is a density. So what this function represents, this red curve that has an input as the horizontal number and an output that's a certain height, that represents mass per unit distance, again, because I have to accumulate across distance in order to achieve mass or probability based on these two ideas. It's mass per unit distance, and that's just another way to say it's a density. If we want to be more specific, we might call it a linear density. So what do we call this red function over here? We call it a probability density function, or a PDF. And what's the idea of a PDF? So let me say that this is a function f of x, where x is my independent variable, and then my output is f of x. So f of x is some algebraic structure that describes this curve in 2D space. Takes an input, yields an output, and the collection of a bunch of inputs associated with their outputs gives a curve that looks like this. So what does f of x mean then in terms of probabilities? Well, what it means is if I have some number here, let's call it a. Again, probability x equals a. I mean, that's not an interesting question to ask, right? That's just 0. So I'm not super interested in that. And it's certainly not f of a, just to be very clear about that. Probability x equals a is not, that's not what f of a gives me. That's not what this vertical value gives me. So what does f of x represent? What is f of a then? Well, what I could think of here is if I took an interval a little bit to the left of a and a little bit to the right of a, we would typically think of these as being a very little bit to the left and a very little bit to the right. But just so we can see it a little better, I'm going to go a bit further to the left and a bit further to the right. But typically we think of these as being very, very close to a. I'm going to go a distance that I'll call epsilon to the left. This is epsilon, the Greek letter E, the Greek letter short e, depending on who you ask. Maybe eta could be like the long E, but this would be the similar Greek letter to RE. So we're on the left side here at a minus epsilon. We think of epsilon as a small positive number. And on the right side, we're at a plus epsilon. I could look at the area under the spread curve above the x-axis, and in between a minus epsilon, a going just a tiny bit to the left, and a plus epsilon going just a tiny bit to the right of a. So I might be interested in the question, what is the probability that x is between a minus epsilon and a plus epsilon? What's the probability that x, our random variable, falls really, really close to a, between a minus a tiny bit and a plus a tiny bit? And here I can say, well, I have a red curve, but if I made epsilon really small, again, I can't draw it really small because it'd be really hard to see on the picture. But if I made epsilon really small, from a minus epsilon to a plus epsilon, the height of the red curve would be approximately constant. Now, of course, when we look at it here, because epsilon's big, it doesn't look constant at all. But if we zoomed in, if we squeezed in our left and right bounds really close to a, the height would barely change over that interval. I could estimate then this area, instead of being a complicated area with three square sides, three flat sides, and a rounded top, I could estimate it just as a box. That wouldn't be a terrible estimate, provided epsilon is small. This is approximately, the base of the box is 2 epsilon, and the height of the box would be f of a. Or if I want to change my units a little bit, because that's kind of 2 epsilon is kind of annoying, I could go epsilon over 2 to the left, epsilon over 2 to the right, and then just get rid of this 2 over here. So this is actually what f of a represents. It says if I accumulate area really close to a, then the probability looks like f of a times the interval over which I did the accumulation. And this is for epsilon small positive. This is what f of a means. It's fairly technical to say what f of a means, right? It's not very technical to say what a probability means in discrete probability distributions. That's fairly simple. If I say it's a ferrous-excited die and I say there's a 17% chance of rolling a 2, like that's pretty straightforward. If I say I have a probability density function given by f of x, what does f of x mean? It's much more technical to say what it actually means. So the keys are, to add one more, we're dealing with PDFs. not PMFs. So the keys are number one, in the continuous world, when we're dealing with PDFs, probability density functions, these smooth curves. Number one, probabilities correspond with areas, which again, we could have forced the issue in chapter 5, but it's, you know, at the surface level anyway, it's seemingly very different than chapter 5. Related to that is that the probability that the random variable equals any particular number is 0. Again, just in the continuous world, this does not apply to the discrete world at all. So the types of questions that we ask that are interesting are, what's the probability that X is in some range, some interval, A to B, or bigger than A or less than B, something like that. And the way that we represent our probability distribution is not as a probability mass function where we enumerate each of the outcomes and their associated probabilities, but we enumerate, in a sense, through a graph, each possible outcome and its density, the kind of instantaneous incremental contribution to probability from that outcome. And in a very technical sense, this is what the PDF actually means. Okay, so let's move away from this abstract stuff and move to something a little more concrete. Let's look at a particular continuous distribution, the uniform distribution. So the uniform, let me zoom in here just a little bit, make it easier to read. The uniform distribution, when we have a random variable that's continuous, often we describe its distribution with this little tilde that says X kind of is distributed as a uniform distribution. And the uniform distribution has parameters, the same way that the binomial or the Poisson distribution has parameters. The parameters here are either just the numbers A and B, or you can think of it as the interval A to B. What does the uniform distribution look like? What's its PDF? F of X equals C, a constant height for X in closed A to B, and 0 otherwise. Well, I need to rewind for 1 second. There's one detail I forgot to mention. F of X, of course, has to be bigger than or equal to 0 for all X. I forgot to mention that up here. Of course, this has to be true because F of X is going to accumulate to get probability. If F was negative anywhere, I could accumulate near where it was negative and get negative probability, and clearly that doesn't make sense. Or, I mean, just me saying that something doesn't make sense to me doesn't mean that it's necessarily right or wrong. So if we want to go a level more foundational than that, we can say, well, we constructed this curve off of something like a histogram that we just kept cutting down. And of course, these heights of these histogram blocks, these are counting numbers, these are frequencies, they have to be non-negative. So my PDF has to be non-negative everywhere. So my PDF is constant for X between A and B and 0 otherwise. So here I have the real line. I have 2 points A and B. My PDF is 0 outside of here. It's at a constant height. We'll just set a y-axis here. It doesn't much, A and B don't have to both be positive, but I'll just set the y-axis there. So this is at height C between A and B, and then height 0 again to the right of B. And often when we have a jump like this, we'll put some dotted lines in. Now, what is the total area under my curve? So if I asked a question like, what's the probability that minus infinity is less than x, less than big X, the random variable less than infinity? Well, I can see that to the left of A, I don't accumulate any area because the height is 0, and same to the right of B. So this is the same as asking the question, what's the probability that X is between A and B? Well, this is just the area under the red curve, or in this case, just horizontal line, between X equals A and X equals B. It's just this area. But nicely enough, I see this area is just a rectangle because that curve that gives my PDF is just a straight line. It's easy for me to use geometry to calculate this. This is a rectangle with height C and with width B minus A. So the total area is C times B minus A. Now remember back to chapter 5. I had a law of total probability. I said that the sum of the probabilities of all the outcomes has to be 1 in the chapter 5 context. Because if I run the probability experiment, something has to happen. What's the equivalent notion to that here? If I say the sum of all of these frequencies, these relative frequencies, has to be 1. When I start splitting bins in half, I'm just reallocating things. I'm not changing the total amount of frequency, right? Maybe this went from a total of 25% to 11 and 14, but I still have 100%. I'm just splitting it up a little more in a little more refined manner. When I split again and again and again, I still maintain that total probability of 100%, that total area of 100% or 1. So my total area under a PDF must be 1. So if I let A and B as well as C be kind of free variables, if I say you can pick them any way you want, you could pick A way to the left, B way to the right, and C really tall, and get an area bigger than 1. So typically what we would do is we would take A and B as free variables, so you can pick A and B wherever you want. That sets a certain width for the base of the box, and then I can adjust the height. I can solve for C in terms of those. So if I set C times B minus A equals 1 to impose the requirement that to be a valid PDF, you have to have total area 1, I get an equation that I can solve for C. So for this to be a valid probability density, this height must be 1 over B minus A. I can pick the start, the left endpoint, and the right endpoint of the box anywhere that I want. But once I pick those two, that sets the height of the box to make the total area be 1. So this is our uniform distribution. This is the most straightforward probability density function because it's just a straight line. It's just a horizontal straight line. We could also have one that's like a tilted line where we have maybe a triangle or a trapezoid. We could also use geometry in that situation. We could use geometry there as well to figure out, what the heights need to be or whatever it may be. Okay, so let's look at an example. Suppose that a certain train, like a subway type train, arrives every 15 minutes, but we don't know the schedule. We don't know when it last arrived at the station. Keep in mind, we're also working under probability theory. So if we say it arrives every 15 minutes, it does. it doesn't get broken down. The driver doesn't, fall asleep at the wheel and stop it in in the parking lot or something. I don't know where they park trains, the train station, I guess. So it arrives every 15 minutes. We walk up to the platform. We might have walked up to the platform just as the train is rounding the corner, and we have to wait basically 0 time for the train. Or we might have walked up to the platform just after it left, and we, just barely didn't see it leave. And we might have to wait basically 15 minutes, or we might have to wait anywhere in between. We don't know where we're at in the train cycle. So we're going to choose to model this, the amount of time we have to wait, as a uniform random variable on the interval 0 to 15. If all that I know is that I have a continuous random variable that's bounded above and below, the most sensible distribution to use is the uniform. We talked a little bit about maximum entropy distributions, and in this case, the uniform is the maximum entropy distribution for this scenario. So it's, in a sense, imposing the least modeling assumptions on the system. So let's compute I have the answers in here already. Let me erase those. I didn't catch that when I copied it over. So spoiler alert, I suppose. Okay, so let's compute a couple of these probabilities. And before we do that, let's draw a picture. Let's get an idea of what this looks like. There's X. And we're interested in the interval 0 to 15, which are the possible waiting times. We're uniform on 0 to 15. So we have our PDF has height 0 to the left of x equals 0, and height 0 to the right of x equals 15. What's the probability that I wait between 16 and 17 minutes? 0. It's 1 unit wide, but 0 units tall. That's an area of 0. What's the probability that I wait between -3 and -4 minutes? Same thing, 0 probability because of the 0 height. And then I'm at constant height in between 0 and 15. What does this constant have to be? 1/15. So my PDF is a box with the base going from 0 to 15 and the height of 1/15. What's the probability x is less than 15? Well, probability x is less than 15, I guess this would be like at the right endpoint of 15, but going all the way to the left down to negative infinity. But this is really just the same as the probability that x is between 0 and 15, because all of the stuff to the left of 0, all the PDF, the piece of the PDF to the left of 0 has height 0. So it doesn't contribute any probability. What's the probability x is between 0 and 15? Well, that's the area of this whole box. That's the height, 1/15, times the base width, 15, is 1. Let me undo some of this to get my scribble off of there so I can reuse the picture. Or we see 1 or 100%. We will always wait less than 15 minutes for this train. Right? Again, under our model. In real life, does the train maybe break down and we have to wait 30 minutes? Maybe. That's something that's not covered under our model, though. Now, you might notice that this is a strict less than. If I had asked, what's the probability x less than or equal to 15? That's really just the same question. Why is that? Well, because that's probably x less than 15 or x equal 15. I think we can agree on that. These have to be mutually exclusive. We can't be strictly less than 15 and also exactly equal to 15. But this is 0. Probability x equals 15. Remember, just in the continuous world, not in the discrete world. In the discrete world, this would probably be a non-zero number. But in the continuous world, this is 0. So we see that the probability of being less than or equal to a number versus probability of being less than a number, it's the same thing in the continuous world. In the discrete world, we have to be very careful about less than versus less than or equal to. In the continuous world, I just basically always use strict inequalities because they're quicker to write. What's the probability x is between 3 and 5? So here I have 3 and 5. And I'm looking for this area between 3 and 5. That area has a base width of 2, 5 minus 3, times the height of 1/15, or 2/15. What if I ask the question like, what's the probability that x is between 1 and 3? This is 1/15 times 3 minus 1, also 2/15. What about probability x being between 10 and 12 or 13 and 15? Same, 2/15. So there's a sense in which the characterization of the uniform distribution is that probabilities only care about the size of the interval, not the location of the interval. As long as the size of the interval is 2, roughly speaking, as long as the size of the interval we're asking about is 2, then we get the same probability, 2/15, whether it's 1 to 3 or 3 to 5 or 10 to 12 or 13 to 15. And we do have to be a little careful here because I could come up with an interval of size 2. And I might be tempted to just write 2/15 for this as well. But here I might notice that I have a situation where I kind of straddle a breakpoint. I see I have an interval from 14 to 16. From 14 to 15, I'm on one piece of the PDF, and 15 to 16, I'm on another. How can I figure this out? Well, I suppose I could break this into two scenarios. I could split my probability at 15. Of course, if I'm between 14 and 16, I'm either between 14 and 15 or between 15 and 16, and that's mutually exclusive. I'm not worrying about what happens exactly at 15, again, because I don't really care about probability x equals 15. It has 0 probability. That or for mutually exclusive events can be split into a plus. Probability that x is between 15 and 16, that has height 0 times a base width of 16 minus 15. So this is actually probability 0. I can never wait more than 15 minutes for the train under this model. This piece has probability 0. And then probability x is between 14 and 15 has, on this interval, my PDF has height 1/15. My base width for this rectangle is 15 minus 14, or 1. So this turns out to be 1/15. So we do have to be a little bit careful when we're looking at intervals. If the full interval is in between A and B, in between the start and end on our uniform distribution, then we can make the statement that we only care about the size of the interval so long as the full interval is in the interval A to B. If it's outside the interval A to B, then I have to be a little more careful. Okay, so what about probability x less than 5? Again, if I come up here and I have x equals 5, probability x less than 5, the meaningful area is the area between 0 and 5. I have height 1/15 times base width of 5 minus 0, or just 5. So 5/15, or 1/3, or about 33%. So about 33% of the time, or a third of the time, I will have to wait less than 5 minutes for the training. What's the probability x bigger than 10? Well, that's also a 5-minute window, right? From 10 to 15. That's also 5 times 1/15, or about 33%. What about 7 to 12? Having to wait between, the probability of having to wait between 7 and 12 minutes. That's also an interval of 5 units. That's between 0 and 15, 33%. What about 12 to 17? Well, that's an interval with 5 units, but it overlaps the right endpoint. So I'd have to be a little more careful there. Let's say the probability x bigger than 20. That's, of course, 0 out here at 20, going all the way to the right. We have 0 height, there's 0 probability out there. Okay, so let me try to erase this without messing everything up too much. I think it's gonna just redraw it. So last question then, what is my expected value? Well, up here, quite a while ago, I talked about expected value being like a weighted average, or like the balance point, or like the center of mass between probabilities. So what if I, instead of thinking of probabilities as being like point masses, being all the mass located right at a specific point, what if I thought of this as being like a smear of probability across across this interval 0 to 15? This smear of probability has the same density everywhere. It's the same thickness everywhere. So it's a little bit like if you got some peanut butter on a knife or something and held out a slice of bread flat and smeared the peanut butter across, and you did a really good job and kept it the same thickness all the way across. Where would the center of mass be for this? Where would the balance point be for this kind of rectangular chunk here? It's got to be right in the middle by symmetry. This has got to be the expected value. 7.5. It's got the same amount of mass to the left as to the right, with the same moment, with the same center of mass on each side. So although I suppose if I'm arguing how to find the center of mass given the centers of mass that I already know, that's a little bit of circular logic there, or a lot of circular logic. But here, by the symmetry, the center of mass is right in the middle at 7.5. On average off the weight, 7.5 minutes. Are there any questions on the uniform distribution? So just like in discrete probability distributions, we had some kind of free form, I suppose, distributions where we could just list out our outcomes and our probabilities, but we had some canonical distributions. We had the binomial distribution, the Poisson distribution. In continuous random variables, because things are just harder to work with, because we're trying to find areas under curves that might be fairly messy, and we can't always use geometry directly to do that, we work actually a lot more with canonical distributions than with just kind of, flying by the seat of your pants types of distributions. So, okay, a little note down here on the expected value, but this is what it is. So some canonical distributions, continuous. The uniform is probably the simplest one. Another important one is the exponential. It starts at 0 and looks like this. It's an exponential decay and has 0 height to the left. So it's like f of x equals 0 for x less than or equal to 0. And it's, what is it? It's lambda e to the negative lambda x for x bigger than 0. You always have to think a little bit to get the constants right. And of course here, lambda bigger than 0. Lambda is just some other Greek letter, the Greek letter L. Unfortunately, in probability theory, we use a lot of Greek letters. So the exponential distribution is kind of important because it is, number one, it's right skewed. It has, I didn't draw it very well, but this tail gets really small, but goes on forever. So it's right skewed. So it's a good counterexample that you'll see pop up later on in this chapter 6 when we talk about testing for uniform distribution, or for testing for normal distributions and so on. There are some others that are important, like the log normal distribution that comes up in finance. There are tons and tons of these distributions. But then perhaps the most important of all of them is the normal distribution. It's one of these canonical distributions like the uniform or the exponential. It's a family of curves that have a parameter or parameters that you can pick. So for my uniform distribution, if I only made it uniform 0 to 1 and that was my distribution, period, end of story, that wouldn't be super good for modeling things, right? I would have a heck of a time modeling something on an interval 0 to 15 if I could only use 0 to 1. So I give some freedom in A and B and my left and right endpoint. Same with my exponential. I might want to fit this to a certain real world application. I might want to change lambda, the decay rate, to fit some application better. The normal distribution is similar. It's a family of curves. It is what's described by the bell shape. When we talked about that, it has an axis of symmetry. It's symmetric about its mean. It has a peak in the middle, and then it tails off to the sides. That's kind of its characteristic, the normal distribution, the bell curve, the Gaussian distribution. And this is its PDF. So it has the bit doing the work, looks like e to the minus x squared, which is what makes the bell piece. if we build off of that and we get e to the minus x minus mu squared over 2 sigma squared, that's building in some parameters. We're going to look at what changing mu and what changing sigma does. And then we have to keep the total area under the curve equal to 1. So that's where the 1 over sigma root 2 pi comes from. This constant on the front makes the area under the curve be 1. So there's a couple of things we might notice here. Just get rid of this for the time being. Get rid of that too. A couple of things we might notice. The symmetry means that the mean, the median, and the mode, the symmetry and the peakness combined mean that the mean, the median, and the mode are all equal. So the measures of center, well, these three measures of center anyway, are the same for this distribution. That's kind of nice. Something that can sometimes trip people up is that the normal distribution is defined for all real numbers x. And we often use it to model something like maybe the heights of people or something like that. So maybe if we're looking at the heights of men, maybe this is like 5'9" in the middle here. So technically we're saying that there's some probability that a guy is between 10 feet and 11 feet tall, or for that matter, between 100 feet and 110 feet tall. There's some non-zero probability of that happening under our model. Even more strangely, we're saying that there's some non-zero probability of a guy being between -2 feet and -1 foot tall. That's not even a sensible thing to say, but it's a non-zero probability under this model. But again, all models are wrong. Some models are useful. In practice, these tails, they go to 0 like e to the minus x squared. E to the minus x goes to 0 pretty fast. E to the minus x squared goes to 0 extremely fast. In fact, it goes to 0 so fast that that it makes modeling things with a normal distribution sometimes actually problematic. If you model things in finance with a normal distribution, it turns out that strange things happen in the financial markets because of things like positive feedback, and fear begets fear and greed begets greed and so on. Because of that structure, strange things happen too often to model things with a normal distribution. You have to use a different distribution or different distributions that are called heavy tail distributions. So the normal distribution, these tails go to 0 extremely fast. So even though the probability of under this model of somebody being more than 100 feet tall is technically positive, it's such a small positive number that it's unimaginably small. Same thing with what the model says about the probability that someone is a negative height tall. If it's like 10 to the minus 100th is the probability or something like that. Okay, I mean, we could balk at that. We could say, oh, that's a positive probability for something that's impossible. But it's a much more useful model to just keep the nice algebraic structure and just say those tails are so incredibly small that we just don't care. So the tails go to 0 extremely fast. And once again, probabilities are represented by areas. This might bring up another question as, wait, if this distribution is infinitely wide, how can it have total probability 1? How can the total area under it be 1? And for this, I like to just present kind of an analogy. This isn't this exact problem, but as an analogy, if you imagine if you had, say, a whole pizza or something like that, there's one pizza, and you said, okay, we need to feed a bunch of people, so everybody line up, and when you get your turn, you can take half of what's left, but no more. So the first person, they got lucky, they get half a pizza. The next person gets half of what's left, or half of a half, 1/4. The next person gets 1/8 of the pizza. The next 1/16, and so on. we're adding positive numbers forever. We're adding together infinitely many positive numbers, but it equals a finite number. I think we can see that we'll never run out of pizza. I mean, maybe at some point we have to debate what it means. You know, if you have one molecule of cheese or something, does that still count as pizza? I suppose you can't even have a molecule of cheese. You could have like a molecule of some amino acid or something. But we see that we can add together infinitely many positive numbers and get a finite result, so long as those numbers we're adding together get small enough fast enough. And again, remember that when we get to the tails, these areas go to zero extremely fast. They go to zero much faster than even this sum here. This goes to zero like 2 to the minus x, and this goes to zero like e to the minus x squared. There aren't too many things that go to zero faster than this normal distribution function. Okay, so we can actually add up all the area. It's not an easy thing to do. Like you need, I guess you need Calc 3 for it. So it's certainly not something that we're going to work through in this course, but it can be done. So we're going to take on faith that the area under this curve is 1. And let's look at what happens if we change mu and sigma. So let me start with a normal distribution. We said that we're symmetric about the mean, so that tells us where mu is. I suppose technically that doesn't tell us where mu is, because all that I've said so far is that mu and sigma are parameters for this. But I think we can probably infer that mu, the parameter, represents the mean, and sigma, that parameter is called sigma because that represents the standard deviation. So that is correct. Mu is right here in the middle. Something we might notice about this function is that it has an inflection point. In fact, it has 2 of them. So in the middle here, it's like curved down. It's concave down. It's kind of like a mountain, like the top of a mountain. At the ends, it's curved up. And there's a point on each side where it switches from being curved down to being curved up. Those are called inflection points. And those occur at 1 standard deviation away from the mean. Again, you could use calculus to show this, and this is a Calc 1 problem. So if any of you have taken Calc 1, try to show this. So this is how the mean and standard deviation affect the distribution. If the mean increases, then to make it a little more clear, I'll write that down below here. If my mean increases, what effect does that have on the distribution? The distribution is going to look the same. Trying to draw it as similarly as I can to up above. But mu has shifted over to the right. But our inflection points are the same distance away. Our standard deviation has not changed. So mu is what we call a location parameter. Mu sets the location of the center of the distribution and moves the distribution left and right when you change mu, but it doesn't change the shape of the distribution. So on the other hand, if we have a distribution like this, if I were to increase sigma, maybe I'll do this in red. Let me zoom this in a little bit. I feel like I'm pushing my luck. I've had zooming and copying work pretty well this morning. So, but what if sigma increases from what it is here in black? Well, now all of a sudden my inflection points have to get wider. Mu stays the same. I didn't change mu, but my inflection points, my points where I go from concave up to concave down and vice versa, have to be further away from mu. If I did something like this, I can see that that can't be what the solution looks like, right? Because remember, the black curve has area 1 underneath of it. If my red curve is like overall above the black curve, because I've just pushed everything out, well, that can't be right, because now my red curve has got to have area underneath of it of more than 1. So I've got to have a shape like this that's pushed out to the sides, but also becomes a little bit shorter to compensate for that that increased area. So I have greater area in the tails. Oops, I started a little too late there. Greater area in the tails. But then I have to have less area in the middle to compensate for that. And this, I think, is consistent with what we'd expect from a situation where the standard deviation is increased, where it's now more likely for us to be far away from the mean under the red curve than under the black curve. I see greater area far away from the mean, and I see, relatively speaking, less area close to the mean. The red curve is below the black curve there. When I have a bigger standard deviation, getting things away from the mean is more likely, and getting things close to the mean is a bit less likely. And then vice versa, if standard deviation decreases relative to the black curve, things have to pull in, but again, they can't just pull straight in. Otherwise, we end up with total area less than 1. We have to pull in sideways, and then we have to get taller to compensate. So maybe my new standard deviations are like here, and I have something like this. So lower standard deviation squeezes more of the probability closer to the mean and less of the probability out in the tails. It's more likely that under a lower standard deviation, it's more likely we get a result that's close to the mean and less likely we get one that's far away from the mean. This kind of tall, skinny, low standard deviation normal distribution is called leptokurtic. So generally, kind of the pointiness or the humpiness of the distribution is the kurtosis. It's in some of these things with descriptive statistics, you'll see skewedness listed as a number and also kurtosis listed, and that's what kurtosis is the humpiness of the distribution. And the high standard deviation is platykurtic. Probably not super important to know those terms, but if you hear them thrown around, you know what they mean now. Kurtos meaning humped in Greek, lepto meaning thin or skinny, I think, and platy meaning flat, like platypus. So, okay, so we'll leave it there for today. Next time we'll look at the standard normal table, and we'll look at using that table, because eventually we're going to want to find areas under this curve, right? And this is certainly not a nice algebraic structure that we can easily find areas under, like we could for the uniform distribution. So how do we find areas? Well, we need to use a pre-computed table of values, the standard normal table, to find those areas. And that's what we're going to work on next time. We're going to go through lots of examples of using that table, how to use it to find areas under these normal curves.